Thank you once again for coming to tonight's talk, and let's please welcome Professor Eilat Glikman.
Thank you. Thank you. Thanks, Chris. Can everybody hear me? Volume's good? Okay, great. So it's a pleasure to be here. This is sort of the love of my life is talking about black holes, so it's really fun for me to be able to share this with my community. I promised that I would keep the equations to a minimum, but we have to get started with an idea, a concept, to get started and to really understand what is a black hole with this concept called the escape speed or the escape velocity. So I promise this is the only equation that I'm going to have in my talk, but I thought we'd get it out of the way and kind of get our feet grounded into the concept. So this idea of an escape speed is the idea that if I throw something up in the air, like this stick figure is doing with an apple, right? And I give it some speed, some launch, it's going to make an arc, it's going to reach some maximum height, and then it's going to fall back down. This equation comes from the law of gravity. If I just manipulate that law of gravity, I can derive this equation. And what it tells me is that so long as I give something some speed that's less than the escape speed, gravity wins and it brings the thing back, okay? There's a special speed that I can give it to put it into a circular orbit, but anything beyond that, sort of once you get to the escape speed, anything beyond the escape speed, this stick figure is able to launch that apple away from the Earth, never to return again. Now we know how to do this, and we've launched rockets into space with a speed of 25,000 miles per hour or greater, which is the escape speed from Earth's gravity. And we've launched rockets, and we sent Voyager and other missions out into space, leaving Earth's gravity, okay? The important thing about this equation is that it depends on two things. So it depends on how massive the object is. So in this case, we're talking about the Earth, so the Earth's mass, and how big it is, the radius, okay? So if the object is very, very massive, it will have a large escape speed. And when you divide by a small number, you get a big number. So if the object is very compact and small, and you manage to shove a lot of mass into a small thing, you also get a very high escape speed. So keep that in mind. Big things require a large escape. Massive things require a large escape speed, or compact and small things where all the mass is shoved into a small radius. You got to give it a lot of speed to get away. Okay? So those are kind of like the things that run our show. So that's just comes straight out of gravity, and we know how gravity works. But nature kind of threw in a monkey wrench to the whole story. You can't just go as high a speed as you want. Nature tells us there is a maximum speed that cannot be exceeded by anything. Okay? We know this is the speed of light. Einstein and others showed us that nothing can go faster than light. And so that kind of limits what's happening with that equation. So let's talk a little bit about how things shine and how we're able to see things in the universe, given the fact that light travels at this finite speed. So if I'm a star, if I'm looking at a star, and light leaves the surface of the star and shines away, the fact that I can see stars thousands of light years away, let's say, means the light was able to escape, right? It escaped, and it went in a straight line and came to me, and it entered my eyeball or my telescope, and I was able to observe it. So to see something, light must be able to escape the thing, okay? And for many, almost anything that you can see, of course, the escape speed is much lower than the speed of light. Light has no problem. So that's a star. That's up there in labeled A. And so let's look at this equation and see how it kind of relates to different types of objects. So if you have a star, you have a big radius. Stars are huge. The sun is huge, right? And a relatively small mass. I know the sun is massive compared to sort of the Earth and our experience as orbiting the solar system, but we're about to encounter some enormous things. So relatively, the stars have small masses. And so a relatively small m, but a kind of big R means we have an escape speed that allows the light to get away, and it's no problem. There are these other very interesting objects called neutron stars. They're kind of the most dense and compact stars that exist in the universe. A neutron star is a star that has the same mass as the sun, but squeezed down to like the size of Manhattan. So if you took all the mass of the sun and you squeezed it down to just a couple of miles in diameter, you would have a neutron star. And in a neutron star, the light can escape, but notice how its lines are a little bit curved. It kind of reminds you of the shape of that apple as I was throwing it up into the air, right? You can even have more dense neutron stars, and so their light can escape, but it's curved even more. But what if you have a system where the radius is so small and you've managed to pack a ton of mass into that tiny, tiny radius, you get to a point where this equation gives you a number on this side that's bigger than the speed of light. And that means light cannot escape. And since nothing can go faster than light, that's it. The light is literally trapped and cannot leave. And so just like the apple came back down, the light cannot leave the black hole. So that's the definition of a black hole. That's what a black hole means, okay? And so I just love to zoom in on this catastrophic situation. Here's the thing, right? This is an artist's rendition of a black hole. This was a hypothetical idea. This was sort of a wackadoodle game that was played for about 50 years. The concept of black holes was introduced about 100 years ago. And for a very long time, it was just kind of like fun. It was math. It was hypothetical. It wasn't a real thing. Nobody thought it could possibly be real. Surely some new physics would come along that would tell us, no, you can't do that. And the reason it's reasonable to understand why people would think that, because, for example, for the sun to become a black hole, you'd have to squeeze all of its mass into a diameter of 3.7 miles. That's kind of hard to comprehend. What happens to all that matter? How do you do that? If you wanted to squeeze the Earth into a black hole, you'd have to make it this big, less than 2 centimeters in diameter. Right? So it's just incomprehensible. And so it's not crazy to understand that people thought, well, this is a hypothetical idea. One day we'll figure out the physics and we'll know why this can't be. It's just a concept. And this was so until 1963, when an astronomer at Caltech by the name of Martin Schmidt made a very interesting discovery. So 1963 was a time when the technology in radio astronomy started to get good enough. So when I say radio astronomy, picture in your mind those giant radio dishes that you've seen with the big antenna. And so, of course, we can use them to communicate, but we can also point some of these radio dishes into the sky and take pictures of radio waves that are being emitted from objects in the universe that are telling us something interesting about their physics, okay? And at this time, in 1963, you were starting to be able to localize the light that you saw in the radio to very precise positions. So precise that you could say, that radio source that my radio dish is telling me is over there, I can correlate it to a star that I can see with my eyeballs, okay? So the fact that we can take pictures with visible light, with telescopes, and then say, but the radio source coincides with that object, allowed us to start to understand, why would something like this be giving off radio waves, okay? So here's the radio image of this object. It's called 3C273, because astronomers love to give things lots of funny names. So 3C273. And it corresponded to a visible star, something that looked like a star in the sky. And so these are the two things that we're seeing. It's interesting, this is a much more sensitive image than the one Martin Schmidt used, and we see this little kind of protruding jet. I'll mention jets later on, and this is the radio emission from that jet. So anyway, this was kind of an unusual thing. I should say regular stars, like the sun and other stars, they're very feeble in the radio. So we can study our own sun in the radio because it's nearby, but in general, stars are not radio sources. There are sort of several handfuls, and they're interesting because they're weird and they give off radio and what's going on with these things. But by and large, stars don't give off radio, and so this was unusual and spectacular and exciting. So what do astronomers do when they find an unusual and spectacular and exciting thing? They take a spectrum. What is a spectrum? So if you ever see the cover of Dark Side of the Moon, that's a spectrum. A spectrum is when you take light and you pass it through some kind of material, like a prism or a grating or something that disperses the light into all of its colors so you can see the different parts. I like to say that a spectrum is a picture of a rainbow. We had a beautiful rainbow the other day. I don't know if you guys saw it. Just a couple of days, was it yesterday or 2 days ago? Anyway, raindrops will give you a spectrum of the sun, right? And so astronomers pass light from astronomical objects through their telescope. They put a little prism or some kind of dispersive medium in the way, and then a rainbow comes through, and they take a picture of it. And what you get from that information is you look at the light and you say, how much red light am I getting? How much blue light am I getting? How much yellow light? You compare the light at the different colors, and you learn something about the physics of the thing that you're studying, okay? And so and then usually we make a graph out of it because we like graphs. So here's a graph of the spectrum of 3C273, so the blue line, right? And down here are wavelengths that correspond to the colors. Now, it's kind of worth noting that what your eye can see spans these wavelengths over here. Of course, light kind of, traverses a wavelength range that's far broader than what your eye can see. And of course we have detectors that can take pictures of those wavelengths as well. And so you have this spectrum over here. And what Martin Schmidt noticed in this spectrum, well, first he noticed that there was some emission that got brighter as you looked at bluer colors. So there's more light coming out in blue than in red. So these are kind of blue objects, so to speak. And he noticed that there are these spiky things that stick out over here. Those are called emission lines, and they come from atoms. So atoms give off emission lines. They have to do with the electrons jumping down from being excited. And if I were to study, for example, so this is labeled H for hydrogen. So I'll tell you the answer. The answer is these emission lines that we're seeing are from hydrogen, but there's something funny going on over here. So if I had a gas of hydrogen in my laboratory, and I excited it, and I took a spectrum of it, I would see sort of sharp, spiky lines, not where you're seeing them, but where the labels are. So I would see a bright red line, I would see a bright green line, I would see a bright sort of bluish line, and a purple line. So when Martin Schmidt looked at this spectrum, he said, I don't know what I'm seeing. This is weird. Other elements give off emission lines as well. They're in different locations at different wavelengths, but this particular pattern didn't match anything that was known before. Not helium, not carbon, not oxygen, not nitrogen, nothing that had been known at all. No molecules. So he was completely perplexed. And it was sort of this realization that he had in 1963, a couple months after he made this discovery, that he noticed that if he took the number that corresponded to each of these laboratory wavelengths and multiplied them by the same factor, they all shifted into this location. And notice the shift is towards redder wavelengths. So we call that shift a red shift. And I'm going to talk more about what that means. It's incredibly significant. Okay? So Martin Schmidt noticed a radio source with a bright star that's coincident with it that had a high redshift and strong emission lines. And so, he actually found another such source, 3C48, and there was sort of like this big brouhaha in the astronomical community about what these sources are. So the first thing you do when you find something new, and you maybe find a few of them, is you just list what's common about them so you hopefully can piece together what's going on. So the characteristics that we see in these things, we call them quasars. I'll tell you why in a moment. So they look like stars in the visible light, but they are coincident with a radio source. That's the first thing that was understood about them. They have these emission lines, and here's a funny thing. No reason you should know this, but if I took a spectrum of hydrogen in my lab, the lines would not be kind of chunky at the bottom. They'd be very skinny. They'd be kind of sharp and very specific to one wavelength. The fact that they're broad is interesting. I'll tell you more about that in a few slides, but just kind of keep that note in your mind. They're broad emission lines. That's unusual and interesting. They're also very bright at blue wavelength. That has an important significance. And we see that they're at red shifts that are high, sort of unusually high. One more thing I'll tell you about them after they started studying these quasars is that they change brightness. They're not steady. So we're all grateful that our sun just sits there and gives off the same amount of light every day, all the time, because that would be a problem otherwise. Quasars don't do that. They kind of flicker on and off and change. Not quite on and off, but bright and dim sort of thing. And so the first thing they did was give them a name. And they called them quasi-stellar radio sources. That's what the word quasar means. It's a kind of a squish of terms. And so quasars are quasi-stellar radio sources with that list of characteristics. So they listed the characteristics, but then it was like, well, what is this? What's making this? What's causing all of this? And so this is such a, I have to show this slide because it's such a classic sort of, physicist astronomer thing. You find a thing and you're so excited and you're so baffled and you're so kind of like blown away that you convene a conference to talk about it. And so they convened the very first thing called the Texas Symposium of Relativistic Astrophysics. And they gathered all the big names in the field. And these letters here are just letters to the editor from various very important astronomers. I got very excited when I saw this one. This is Ed Spiegel, who was a professor of mine at Columbia. He's one of the original guys. Vera Rubin, who discovered dark matter and totally deserved the Nobel Prize. I won't say any more about that, but it's not cool. She passed away a few years ago, so unfortunately they don't do posthumous prizes. Jesse Greenstein, who was also an important astronomer who passed away a long time ago. But these are kind of like the people who were driving the big ideas. And these are letters to the editor of Physics Today, just remembering sort of fondly how exciting it was to try to figure out what this all was about. And so they spent, I read the proceedings for the first and second Texas Symposium for my thesis, and it was just, it was palpable how excited they were and how confused they were. And there was just, this spirit of understanding and discovery. And so, at the end of the day, they came to realize that only the accretion of matter onto a supermassive black hole can explain all of those observed phenomena that I listed, okay? And I hope to convince you of this. But before I get to that, I just want to give you a definition. So I realize astronomers throw the word accretion around all the time like it's nobody's business, and it's not a common word that people use. So accretion, from the dictionary. It is the process of growth or increase, typically by the gradual accumulation of additional layers, or in our case, matter. So you might use that term in a geological context for sediments and coastal mangroves, or in astronomy, it's the coming together due to gravity. So you have a black hole that has a lot of gravity, and it's pulling matter towards it. It's accreting matter. And that matter will enter the black hole, and the black hole will get bigger, okay? So that's accretion. I'm going to go through those characteristics now and try to convince you what the reasoning is for why each of them tells us that a black hole is going on. I'll actually start with the hardest one. So the radio part. The radio part is still a bit of a mystery. So the fact that the star-like object was identified with the radio source, it turns out, what didn't take long for people to realize this, that even though quasars were discovered in the radio and it's in their name, actually only about 10% of objects give off radio emission. So there's actually way more, 9 times more quasars out there in the universe that don't give off really any radio at all. I have 2 students in the back who are doing summer research with me right now, trying to understand all of this. So they're looking at quasars with and without radio emission and trying to kind of figure it all out. It's a challenge. Nonetheless, in order to produce, so here's an example of a sort of, not quite a quasar, it's kind of a wimpier version of a quasar. We think it's sort of like a quasar that finished its business and is kind of resting-ish. There's a galaxy right here, a galaxy, like the Milky Way, like a giant galaxy. This is its picture right here. And so to scale, with this distance away, are these 2 bright blobs of radio emission that we call jets, for obvious reasons. It looks like, light is being shot out in these jet-like formations, and they give off radio light. This is incredibly sort of dramatic phenomenon. And so anything this extreme requires relativistic physics. Relativistic physics means you're at extremely high energies, extremely high speeds, extremely high masses. And so that kind of hints at black holes, okay? And so the radio emission from quasars is still really not fully understood, but when we see radio emission coming from a source in the sky that's not a star, it's outside of our own galaxy, we have a good sense that it's probably involving some kind of black hole emission, or the black hole activity, I should say. So the radio one is probably the hardest one to convince anyone that there's black holes going on, but the rest are pretty straightforward. So those broad emission lines, here's what you should picture in your mind. You have a black hole that's got a ton of gravity, right? And gravity likes to pull things in. But unless you happen to be in a very special configuration, you're going to go straight in on a straight line, most things swirl into black holes. Just like we're circling the sun in an orbit. So things like to go into orbit, right? And so the gas that's around the quasar, around the black hole, is kind of swirling in, much like I like to imagine water going down a drain, okay? And so this water, this gas, hydrogen gas, is going down this black hole drain at incredibly high speeds. And it turns out that we can use the width of those lines to figure out what the speeds are. And we find that the speeds are more than 1,000 kilometers every second, extremely high speeds. And that tells us what kind of gravity is going on, right? So we can figure out, for example, the mass of Jupiter by watching the speeds of the moons go around Jupiter. It's nowhere near this speed. We can get the mass of Jupiter. You can use the speed of those lines, the widths of those lines, to figure out the speed, to figure out the mass of these black holes. And you get masses that are just inconceivably large, and it implies the existence of a black hole. So these broad emission lines are very telltale signs of a black hole being there. And so basically falling into a black hole is the only way to achieve this phenomenon that you see. I mentioned that the quasars were getting bluer, getting brighter at blue wavelengths when you look at the spectrum. So all of our water faucets have brainwashed us the wrong way. You go to the bathroom, you turn on the faucet, and blue means cold and red means hot, right? Well, to a physicist and an astronomer, that's wrong. So it turns out that cool things give off red light, and hot things give off blue light. Okay, so I love this. This came from like a light bulb company's webpage. And so if you have a light bulb that has a filament with a temperature of 1,000 degrees, it'll give off mostly red light. And if you have a filament that's shining, that's reaches a 10,000 degree Kelvin, it gives off lots of blue light, even ultraviolet light that your eyes can't see. And so hotter things give off blue light, cooler things give off red light. And it turns out that the fact that the quasar is giving off so much blue light in the ultraviolet and in the blue implies more than 10,000 degrees Kelvin. That's how hot the gas is. So you have this incredibly hot gas swirling at incredibly high velocities as it swirls into the black hole. And again, the way you can explain this is with an idea of gas being compressed as it falls into the black hole and it gets to these very high temperatures. Okay, so all of these characteristics are telling us there's something extreme going on that a black hole can explain. I mentioned those redshifts, and I kind of wish, we could do an entire separate talk on the expanding universe and what redshifts mean. I'll try to keep it brief. But we know that the universe is expanding. So this is a little illustration of that. What that means is galaxies are moving further and further away from each other over time. And so as a result, what happens is if something is moving away from me, it experiences something called a Doppler shift, or a redshift. And so when something is moving away from me, its emission lines or its wavelengths get stretched out to longer wavelengths. This is how, by the way, police figure out if you're speeding. They shoot a radar at your car, which is just light, reading light, and it bounces off and it carries with it. The wavelength shifts and it tells them the speed. So that's the method. It's a very good method, and that's how we know the speed of objects as they're moving away from us is we look at the shift in the lines and we get a speed right away. And it was Edwin Hubble who figured out a really interesting relationship. So he measured the speeds, the redshifts for lots of galaxies, figured out how fast they're moving away from us, and then he separately was like, well, how far away are they? And he measured the distances. And what he noticed was they lay on this nice straight line. Things that are further away are moving away at faster speeds. And that's great, because that means that if I can't figure out the distance to a galaxy, because I don't know how, or I don't have the method that I need, I just measure the velocity. Redshifts are easy to measure. The spectra are like, takes like an hour, it's fine. I take a spectrum, I measure the redshift, I figure out the distance, okay? So after using the redshift for 3C273, placed this quasar at such a high speed, it was actually at such a large distance rather, that it was actually the most distant object in the universe at that time, okay? And this is why Martin Schmidt was puzzled for so long, because they knew about redshift, they knew about this diagram, but most of the things were kind of like down here, and all of a sudden this thing shows up here, It was inconceivable that something would be that distant. Now we know that there are things far more distant. 3C273 is one of the nearby quasars these days. But that redshift implied a large distance, okay? And so it tells us that the quasars are not nearby. They're far. They kind of populate the distant universe. And that has an additional consequence. So if something looks bright to you, look at it, oh, there's a bright thing. But if I tell you that it's also extremely far away, then you know that it must be giving off a tremendous amount of light. And so once we knew the distance and the fact that it's pretty bright, that means it's got to be so luminous. What's the physics that can explain so much luminosity coming out of a tiny, tiny region of space? Okay? And it turns out that a typical quasar will put out 50 times as conservative, hundreds, thousands of times more light than all the stars in a galaxy combined. To the point where you can't see the galaxy. That's why they look like stars. It's a tiny, tiny region of space, and you're just blinded. You can't see the galaxy because there's so much light coming out from the center. Okay? And again, extremely hot, compressed gas falling onto a black hole can achieve this luminosity. So it's sort of like you're putting together a puzzle. At no point did I tell you, yes, it's like, the smoking gun of a black hole, but it's a really long list of circumstantial evidence. And this is what we had for a very long time. The last one, I should say, is also very important, and that is that quasars show variability. So this is a plot called a light curve. It's a plot of brightness as a function of time. I believe this is for 3C273. But anyway, most quasars show this kind of brightening, and you see these kind of moments where they flare up. That suggests that there is a small object that undergoes some change, okay? Maybe gas is being swallowed in, or a star gets ripped up as it gets near the black hole, or some extreme phenomenon changes the brightness. And because the thing is compact, the light from the front will get to you first, and the light from the back will get to you not much later. So these things can flicker on the order of hours or a few days, and that gives you a sense of how big they are. It's not like it takes years or thousands of years. And that tells us that it's a very small, tight system. So again, that's consistent with a black hole because we need to pack all that mass into a tiny, tiny, tiny space. So last week I was at, where was I? I was in Boston for a NASA review for the Chandra Space Telescope. The Chandra Space Telescope is an X-ray telescope. And so after all of this, in the 1970s, we put a telescope in space appropriately named Einstein. And since then, we've had many X-ray telescopes in space. And X-rays are the most energetic light that there is. Well, there's gamma rays, but let's forget about gamma rays for a second. X-rays are extremely energetic light. And so they're produced by the most extreme physical conditions, like something falling into a black hole. If you fall into a black hole, you get extreme acceleration, and the luminosity, the amount of light that you put out, goes as the acceleration squared. And so you just get a ton of light coming out from small bits of matter falling into a black hole, or lots of bits of matter falling into a black hole. And so here's a picture of a quasar in X-rays. Now you might be looking at that and going, that looks like a, I don't know, like an old Nintendo or Atari image or something, right? It's very pixelated. And the reason for that is because it takes so much energy, and it is so hard to make X-rays in space that you don't get that much light from X-rays. Most of the sky is completely dark in X-rays. My first advisor in undergraduate, I did a little X-ray project for him, and he said to me, he said, oh, there's so few X-rays in the work that we do that we could give each one a name. So you can name all those little X-rays. So that's kind of, again, a signature of something extreme and rare and extreme going on. So again, when you see X-rays coming from a source in the sky, there's a very good chance that it's coming from a black hole that's accreting, okay? And I put this picture over here of what I'm going to talk about next, which is actually a very small black hole. So the black holes I've been talking about now, I'll kind of give away the punchline. They're very, very large. We call them supermassive black holes. But even small black holes, they give off lots of X-rays too. And so here's a little X-ray image. It's been blurred so you can see kind of more detail. But we call these things microquasars because they're little, but they do the same thing otherwise. So all those characteristics that I just mentioned, they point to the fact that black holes are reasonable. There's phenomena that can explain their existence. There's no kind of like definitive evidence that comes here. But I just want to point out that quasars aren't the only black holes out there. Like I said, quasars are these supermassive black holes. When I say supermassive, I mean 1 million to 1 billion times more massive than our own sun. Supermassive, right? It's a good term. We usually don't have good terms in astronomy, but that one's a good one. So one of the things that I do in my research, what I think about is, how do you get such a big black hole? What had to happen to make something so incredibly large, right? Accretion might come to mind, and indeed, that's probably the answer, but you know, that's kind of flippant. There's details, right? And so we want to know how they got started and how they got to be so big. And since we know that quasars are accreting by gas, they probably have to start a lot smaller. So where would you get a small black hole from? So I see Frank in the audience. Frank will forgive me about my stellar astrophysics. I will give a quick review and not well, because I am definitely not a stellar astrophysicist. But it turns out that the final stage of life of a very massive star gives you a black hole, okay? And so in a very brief nutshell, this is how stars are born and die. You start out with a nebula, which is a giant gaseous cloud in intergalactic space, or not interstellar space. I suppose there's some intergalactic gas, but we're not talking about that. So it's a cloud, a nebula. It's massive. It'll be many, many solar masses in mass, and it'll be huge. But anything massive experiences gravity. So if you wait long enough, gravity will try to pull it together. And actually what happens is it pulls it together, and then it kind of breaks up in fragments, and you get many, many new stars that are born. And every one of those new stars will kind of start to spin a little bit, because it'll have some angular momentum, and it'll kind of contract and spin up. And eventually it'll get so compact, even though gravity wants to win and squish it down to a point, gas has temperature, it has pressure, and all that temperature and pressure is resisting the collapse. And so you have gravity squeezing in, and you've got pressure and temperature resisting, and we call that hydrostatic equilibrium. And the word that matters is equilibrium, which means nothing changes. So the star sits there on something we call the main sequence, which just means it's not doing anything other than turning hydrogen to helium constantly. And it's just the most efficient and steady engine. Our sun will be doing it for 10 billion years before it's done, okay? Some stars do it much more quickly. So the very, very biggest stars do it much, much more quickly, maybe millions of years. And when they're done, they start burning, turning helium into more heavy elements. And then the pressure really builds up, and you start to puff up the star. So it gets bigger and bigger, and then stuff happens, sweep it under the rug, you get a big supernova explosion. So if the star is between 8 to about 25 times the mass of the sun, you get one of those neutron stars that I mentioned at the beginning of the talk. But if it's more than 25 times the mass of the sun, you get a black hole. So you get, and a black hole is not going to be 25 times the mass of the sun because the supernova throws out a lot of the material into space. It leaves behind maybe a few solar mass black hole. But that's a good way to start, and we've seen those. That microquasar is an example of a stellar mass black hole. Okay, so we know they exist. And if that whole story I told you happened to happen in a situation where the black hole, the thing that went supernova, had a companion star that was orbiting it, that companion star will also puff up to a giant one day. And the black hole has a ton of gravity, and it'll start to siphon gas off from that giant star. And it'll start to accrete like a little quasar. And it'll be a microquasar, and it'll give off X-rays, and you can see it in X-rays. And so in fact, here's a picture of the Andromeda galaxy, our nearest neighbor galaxy, in X-rays. This is an X-ray satellite image. It's not Chandra, it's XMM, but the Europeans put one up in space too, and it's a very nice machine. And so this is a galaxy, and all of these bright spots are probably black holes, stellar mass black holes in binary systems accreting, X-ray binaries. So that's one way to know that there are, I just listed a bunch, but X-rays are one way to be pretty sure you've got a black hole. Another exotic way to be pretty sure you have a black hole is something called gravitational lensing. So gravitational lensing has to do with the fact that mass, thanks to Einstein, we know this is true, mass bends space around it. This is true for the Earth too, but it's not noticeable because the Earth is not massive enough for it to be an appreciable thing. The sun does it though, and certainly black holes do it. So here's an interesting thing. When you bend space, it's just like if you take a piece of glass and you bend it, you get a lens. What happens if you take a magnifying glass and pass it over, let's say, a little LED light or something? It brightens temporarily as you go over it, right? You get all that light magnified. So this phenomenon occurs in space. Picture the following. You guys are sitting on Earth in the Milky Way. I'm a star in another galaxy nearby. And there happens to be a black hole between us. As the black hole passes between us, when it's just perfectly lined up, I brighten up. I just go, bloop, I get brighter, okay? And the amount of time it takes for me to brighten and by how much I brighten tells you a lot about the black hole, okay? So here's sort of a schematic picture of this. Here's the black hole. It's moving because things in space move. Nothing is sitting still. There's a star in a faraway galaxy. And so actually, in fact, here we are in the Milky Way. Here's the scenario. And this other galaxy is called the Large Magellanic Cloud. If you've ever been down to the southern hemisphere, which I have not, so I've only seen pictures, but I'm told, and I know, that if you go down to the southern hemisphere, it's a clear night, you look up, close to sort of the southern pole, you see something that looks like a cloud that will move, and there's two of them. One is called the Large Magellanic Cloud, and one's called the Small Magellanic Cloud. They're actual galaxies, small ones. They're about, like a hundredth of the Milky Way, maybe 10th, somewhere between a 10th and a 100th of the size of the Milky Way. And they orbit the Milky Way. They're like our moon, in a way, right? Yeah, it's amazing. And so the Milky Way extends quite far out. So there's, potentially black holes out here. Well, here we are sitting in one of the spiral arms, looking at the Large Magellanic Cloud, looking at a star in the Large Magellanic Cloud. And if a black hole in our own galaxy happens to just cross the path, then there will be this event of brightening that just brightens and dims in a very specific shape. That's the thing that makes it very interesting. If you observe this night after night after night after night, and we've done this. There were actually 2 big experiments that for 5 years stared at a patch of the Magellanic Clouds and just took pictures night after night after night and made these graphs of brightness over time and looked for things that did that. And they found many examples, and they were able to say, oh, based on the width, how long it took, and how high this is, I can tell you it's a black hole. So we found several black holes using this technique. So it's a weird way to find it because you never actually see it, but you must be there. Nothing else can explode. All right, so those are the little ones. Let's talk about some more big ones. Big ones that aren't quasars. So it turns out that, so this is the picture of the disk of the Milky Way. I'm quite certain this picture was also taken down in the southern hemisphere because the galactic center is seen at a higher, sort of up in the sky better than you would see it from here. And so it's just spectacular. It's a very so I'm told. It's a very, very beautiful sort of, the Milky Way is more beautiful from the southern hemisphere. And so deep in the heart, right at the center of the Milky Way, turns out there's a 4 million solar mass black hole. And we know this. We know this for the same reason that we know, well, we know that it's 4 million solar masses for the same reason that we know Jupiter's mass. When we watch something orbit something else, and we can figure out the length of time it takes to orbit and how far away the thing is, that's all you need to know, and you can get the mass of the thing. So watching things orbit is like amazing. I mean, nature gives astronomers little gifts of figuring things out. It's a whole mystery, but occasionally you get like the right stuff, And so if you can watch something orbit Jupiter, you can, like the moons, you can figure out the mass. If you can watch stars orbit a black hole, you can get the mass of the black hole. Now that seems kind of amazing and impossible, and it almost is, except Andrea Ghez of UCLA did this. So she used the Keck Observatory, which is down in Hawaii. Starting in 1992, I'm going to play you a little movie. I'll play it a few times because this is one of the most amazing movies you'll ever see. And so these are all stars, and this cross is what they're orbiting, but there's nothing there, okay? So let's watch and just talk about this for a moment. So this is a time lapse. Notice the years ticking by. Oops. Zooming in. I'm going to watch a star go around. There's another star going around. Now, when the star goes around like this, it's moving at something like 10,000 kilometers per second, some insane speed. There's nothing here, okay? If you use the normal laws of physics that help you figure out the mass of Jupiter and other, orbiting things, you get 4 million solar masses. How do you have something that has 4 million solar masses, but that doesn't give off any light? It's a black hole, I mean, it's just ruled pretty much everything out at this point. And so this is one of the best pieces of evidence that we have. And we're just going to watch it again because it's so good. She's got more recent videos, but she digitized the stars and it looks less kind of real, and so I still love this video. Because these aren't just actual images, this is truly a time-lapse movie of what's happening at the very center of our galaxy. Unbelievably challenging work, just incredible. Okay. So once we kind of, knew that there was a black hole at the center of our galaxy, we launched the Hubble Space Telescope and started looking at other galaxies. And we came to realize that they all have black holes. So every large galaxy, every galaxy that's that you've seen a picture of, that's big and structured with spiral arms or a nice, elliptical shape, they all have a black hole at their center. What Hubble did was it placed a little slit and took a spectrum of the very center of these galaxies, and while you cannot watch individual stars orbiting, you can sort of see what happens to the light as a whole from all the stars orbiting, and you see extreme shifting to the red and extreme shifting to the blue. That means some stuff is moving away from you, some stuff is moving towards you, and you can figure out the speeds. And you get speeds that just the conclusion you have to come to is that there's a black hole. And in fact, you can use the speeds to figure out the mass of the black hole. So for some galaxies in the local universe, we have measurements of the mass of the black hole and other properties of their host galaxies. So it turns out that black holes are sort of like a ubiquitous component. They're a nuclear sort of ingredient of every galaxy. We don't know about the smaller ones like the Magellanic Clouds. Those are sort of now where the cutting edge research is happening. So I can't tell you about them, but it's very interesting to start to ask yourself, well, why the big ones and not the small ones? And how do the small ones get to be big ones? You know what I mean? So those are all the questions that we're still asking right now. But among the big ones, we found something incredible. This happened in about 2000. Some papers came out that showed that there's this really curious relationship. Biggest galaxies have the most massive black holes, and as the galaxies are smaller, less massive, it goes together. Okay, the black holes are bigger in bigger galaxies, and the black holes are smaller in smaller galaxies. So you might be saying, well, big deal. I mean, tall people have bigger feet. That seems to make sense, right? It goes together. But here's the interesting thing. If you want to think about the black hole and how much influence it has in terms of the size of a galaxy in the space, a black hole is like a grape is to the Earth. A black hole to its galaxy is like a grape is to the Earth, okay? So in terms of its influence, in terms of the gravity. So if you're a star way out at the edge here, how do you know about the black hole? I don't know about the grape at the center of the Earth, And so this is a puzzle This is something that astronomers are trying to figure out. This is something I work on. Because it seems that, how do they know to sort of stay on track with each other, these galaxies? Could it be that they grow in tandem? Could it be that whatever it is that makes galaxies grow also grows the black hole? So it's not that they know about each other, but there's like a third party that's regulating the whole performance, And so that idea is actually starting to take favor, and it's something that I work on. And it's the notion that if you take two galaxies and you merge them together, you crash them together, you can grow stars, you can make new stars, and you can grow a black hole. And galaxy mergers are something we see. They're not common, but they're not uncommon either. They happen. So here are some really lovely Hubble Space Telescope images of different galaxies. The whole process is simulated to take about 2 billion years, so unfortunately we don't get to see how it goes. But we see different stages, and so you see two galaxies over here. They're close enough to feel each other's gravity. Over time they'll come closer, then they'll kind of pass through each other and disrupt each other. Every time you see blue, that means there's newborn stars. So you see that as they're merging, they're starting to make new stars. In the process, you have two black holes that show up to the party. They're going to merge too, okay? So that's spectacular. We don't really know what happens when that happens. Like, we don't really have a good understanding. But as the black holes are kind of like going to spiral into each other, they're going to have a very powerful accretion and they're going to grow. And so you can grow the black hole and build stars through a merger process to keep the galaxies on that relationship. So I just couldn't resist. I just want to show you more pretty pictures of merging galaxies because they're amazing. they're absolutely amazing. So these are just Hubble, of course. Here's a cool thing. We're going to crash with Andromeda one day. I don't know if that's cool. I think it's cool. So this is here we are in the Milky Way. Here's the sun. Here's Andromeda. It's going to take about 4 billion years from now, but we feel each other's gravity. So even though the universe is expanding, if two galaxies are close enough to each other, they kind of ignore the expansion and gravity wins and pulls them together. And so there are a bunch of simulations of what this is going to look like, and I can never resist to show this. I think it's so interesting. So here's a bunch of sort of pictures of what your night sky might look like as this merger takes place. So here's Andromeda. It's getting closer. It's getting real close. Now you got this train wreck of a situation going on. New stars are being born. It's a big mess. And then what you get at the end is kind of a smooth blob. That's what happens at the end. All the gas gets turned into stars during this process, and you're left with these galaxies that are called elliptical. And they're beautiful, but they're not as kind of like detailed and interesting. All right, so that's our future, 4 billion years. Another way, so I have two more ways. Another way to see black holes. So up until now, I've been telling you about all the different ways we can see black holes with light, with electromagnetic radiation, right? So we talked about spectroscopy and X-rays and radio waves and all these different things. But there's a whole other way to sort of interact with the universe that physicists kind of brought to life just a couple of years ago. And that is actually probe at this idea of a gravitational wave, okay? So I'll try to kind of explain it in the way I like to understand it. When I think of space-time, the notion of space-time, I try to imagine, like, think of this room. Oh, I love it. The ceiling has a grid, right? You see how the ceiling's all tiles? Imagine a three-dimensional version of this grid. So you have just a three-dimensional graph paper, or like the tiling, okay, that defines the distances between points in space, just like, you would on a piece of graph paper. And that way I can tell you how far apart you and I are, and we can sort of establish where we are and how we relate to each other, okay? Einstein showed us that grid, even though most of the time it's just like a normal flat piece of graph paper where like all the cubes are the same size and so on, if I put a black hole right here or something extremely massive, it'll start to distort and stretch and kind of, change the grid. It'll actually change the distances between things. It'll stretch or compress space, okay? And so the idea of a gravitational wave is just like when matter accelerates, charged matter accelerates, it gives off light. So that's how you get those X-rays. When masses accelerate, they give off gravitational radiation, or gravitational waves. We can't see them because it's not light, but we can feel them. Now they're minuscule, but if it happened right here, it wouldn't be minuscule. Okay? So the idea is that if you have two black holes and they're orbiting each other, they're going to spiral in and they're going to combine. And that spiraling process creates a distortion in space-time such that, I love this kind of graphic, Imagine the Earth. This is an exaggeration, of course, because the whole thing, by the time that signal gets to us from far away, the stretching is like the size of a nucleus of an atom. It's very small, so we're not noticing it. But it's happening. And so what happens is, as the wave passes, it'll swoosh, and then it'll smoosh. It'll change directions. You'll get stretching and then stretching in another direction. And that's what the wave does as it passes through. So we wanted to actually detect this. And so the way we detected it was we built two giant machines, one in Louisiana and one in Washington State. So they're far from each other, extremely far from each other. We call it LIGO, stands for the Laser Interferometer Gravitational Wave Observatory. And it has two 4-kilometer arms that are at exactly a right angle from each other. And the way LIGO works is there's a laser. And that laser leaves the building, and it passes through something called a beam splitter, which is like a mirror that lets in half the light and reflects the other half. So the laser comes in, and the laser's a wave, so everything's in tandem. Everything's crest, trough, crest, trough, crest, trough. And when it goes through, it's still sort of in sync as it passes away. If nothing changes, then it goes to the end of the arm, it bounces off of a mirror, it comes back, and then the mirror kind of allows it to get combined over here in a detector. And you should detect the light. It's like, I broke it up, I put it back together again, it's all good. But what happens if this arm gets compressed a little bit, or if this arm gets stretched out because a gravitational wave passed by? Then the light gets here back sooner than the light on this side. And they don't combine quite the same. And so instead of getting the light detected back as a bright spot, just like it left the laser, you might get nothing, or you might get a dimmer spot. And it might get brighter and then dimmer and then brighter and then dimmer as the lengths of the arms change. Okay? And so that experiment, this LIGO experiment, is literally testing what happens when a gravitational wave passes through and changes the shapes of this contraption. And LIGO turned on, and well, it was going on for a long time, and then they upgraded it so it could actually detect black holes. And not long after they turned it on, both detectors, this is really important, because if there's like an earthquake, the same kind of thing happens. So they have to sort of see the same thing at the same time, or not quite at the same time, because it turns out that gravitational waves travel at the speed of light. So depending on where the gravitational wave came from, it might pass through Louisiana first and then go through Washington. And we have good enough clocks to actually notice the difference. So one of the things that was discovered from the LIGO observations is that gravitational waves travel at the speed of light, just like light does. That was amazing. We thought so, but now we know. Here's what we saw. In Hanford, which is in Washington, and in Livingston, which is in Louisiana, we saw two identical signals of the laser getting brighter, dimmer, brighter, dimmer, brighter, dimmer, and then it kind of did this, which tells us that the black holes are about to merge, and you can actually listen to it. They turned it into sound, and you hear a chirp. Anyway, this is what, if you took Einstein's equations of relativity and predicted what should such a signal look like if two black holes merged, you would see this incredibly faint yellow line that you can't see because it perfectly matches the data. Perfect. Okay, there's one over here too. And the two signals are identical, which tells us it's not a fluke over here or a fluke over there. We feel it. There's a third one of these. It's not LIGO, it's called Virgo, and it's in Italy. And it's not as powerful, but it has been able to corroborate a few of them when it's been on. So, we have good corroboration of this. And so what did these wiggles tell us? Well, the first one, I believe it's this one, told us that a 20 solar mass black hole and a 30 solar mass black hole combined to form a 50 solar mass black hole. Now we know, so, is this seeing a black hole? I don't know, I think so. It's pretty indisputable evidence that, first of all, astronomers have never seen black holes this big. So that's kind of amazing to me, and it's something we don't really understand. So the purple circles here are black holes that have been discovered through X-rays. And those are up to 20 solar masses, but mostly in the few, like 5 to 10. And so the fact that we kind of discovered a whole new population of black holes with masses that we had never seen before is pretty amazing to me. And we keep detecting them. So LIGO's back on, and I follow it on Twitter, and it announces things every once in a while, and it's very exciting. So, so gravitational waves is kind of like having, it's like having another sense. It's like you can see and you can hear. It's incredible. And now for the sort of pièce de résistance, or whatever. It's the final story of this story. the real seeing of a black hole. So you know, this was on the cover of all the newspapers, the fact that we had taken a picture of a supermassive black hole, what, about 4 months ago or so? And I want to tell you about how that picture was made and why it's so incredible. So that picture was made using a technique called interferometry. It turns out LIGO is also called an interferometer. It really has to do with combining light, really, in the simplest terms. That's combining light in different ways using waves is interferometry. But here's the key. The key is that if you have a small telescope, your images are going to be blurry. The size of the telescope matters, okay? So our eyeballs are really small, so that limits how sharp our images can be. If you had a bigger telescope, the same thing, you'd start to be able to see much more detail. So in general, bigger telescopes let you see more detail than smaller telescopes. I mean, bigger telescopes also let you see fainter things because they collect more light, but that's different. Just the fact of the size, just the fact that light kind of is sampled across an entire bigger eyeball gives you sharper pictures, okay? And you don't need all the light to be like, it doesn't have to be a continuous mirror. You just need a large sampling. So if you want to sort of pretend like you have a big telescope, maybe you can use many little telescopes. So if you want to have a big telescope, and it turns out that to be able to see a black hole, take a picture of a black hole, where you actually make out that tiny, tiny size, you need a telescope about the size of the Earth. That's the size of it. So that seems technologically challenging. So here's what you do. There's your Earth. What if you just put a bunch of telescopes on the Earth and use them together as though they are one kind of big telescope? So that's what we did. In fact, we didn't have to build any new telescopes at all. We already had all these telescopes. These radio telescopes, which are sort of ideal for this kind of work, are situated all over the world. And so there's 8 of them, a global network, and they all came together and said, let's do this. And so they all observed the same source and communicated that information, and then the computer reconstructed all of the data into a picture. Okay? So, I mean, I'm simplifying a ton of stuff. The computational work is unbelievable. But it's doable. We understand every step of the process. And so we looked at 2 black holes. And I remember when the rumors came out that, the Event Horizon Telescope is about to make an announcement, everybody was like, which one is it going to be? Which one is it going to be? It was either going to be the one in the center of our galaxy, the one that you watch the nothing go around, right? Or it was going to be something in the galaxy called M87. Turned out it was in M87. So Messier 87 is a nearby galaxy in that it's 55 million light years away. It's actually not that far in sort of cosmological sense. It's about 2 times more, a little more than 2 times more massive than the Milky Way. It's huge. And it's about 3 times bigger in size. It's just an enormous galaxy. And we're pretty sure that this galaxy formed by mergers. Because look, it's got none of those details. Everything's been erased by the merger. It's exactly what you would expect when 2 galaxies, or more than 2 galaxies even, merge together and form this nice big kind of smooth elliptical shape. This is another one of those jets. So we know there's a black hole that's kind of busy doing stuff in there. It's not quite a quasar. If it was a quasar, it would be so bright that you wouldn't see all the stars. But it's a black hole that's kind of like snacking. It's munching on tiny little snacks. It's not like a big, massive quasar that's consuming a ton of water going down the drain like that. And we had estimated the black hole mass to be 6.5 times 10 to the 9 solar masses, but using our image, which I'm about to show you, we confirmed that that's correct. So that's very heartening, too, to know that all of our methods for figuring things out agree with each other. So this was the image that we took, and I have to say, like, I was moved to tears. It was like one of the greatest days of my life. It was just to know that, to be in this field, and to know that this was achieved by humans, it's incredible. I read an article on Slate that they were complaining that it's blurry, so I'll try to disabuse you all of that truth, or that untruth, I should say. So first of all, how good is this image, and what is it showing us? So this is the black hole. It's in here. In fact, it's sort of in there. We didn't quite resolve the exact edge. So the sort of edge, the Schwarzschild radius, so to speak, that point where, where the escape velocity is the speed of light, is a little bit smaller. It's in here. And that would be like Neptune's orbit, I think. Okay, so this is like the size of the solar system, physically. It's kind of amazing. But there's 6.5 billion solar masses squished into something the size of the solar system. And the stuff around here is very tenuous, gas. I mean, extremely tenuous. Such low density, it's kind of hard to even articulate. but it's like it's swirling around and falling in small bits and giving off light. This light is, I believe, 2 millimeters, so it's very long wavelength. It's red light, which tells us it's cool. It's not a quasar. It's not that hot, extreme activity. But we can see it. Here's how amazing we are as humans. We took Einstein's equations and we predicted what we should see. And this is a simulation. So when you're a theorist and you simulate things, you can pick the best resolution. You don't need to build a giant telescope. Just tell your computer, tell me everything I could possibly know. And you see all this gorgeous structure and all this beautiful stuff. But here's the best part. They blurred it to the resolution of the actual image. And it's like, come on, can we do better? That's amazing, right? So I love this. The other thing that I think most people don't know about this image is that we are now getting a movie. So, I mean, we're staring at this still. And so here are different images over time. So not only are we learning about the shape and the structure of what goes on around a black hole, but we get to learn what changes about this black hole over time. We get to see how things move into, you're already seeing different changes just over the course of a few days. And so it's very exciting to sort of be able to make a movie. Okay, so here's my chance to disabuse everyone of the blurry remark. This picture is 1 pixel on the Hubble Space Telescope's camera. And we are now going to zoom in to see the black hole with respect to the size of 1 pixel on the Hubble Space Telescope camera. A colleague of mine did this and I absolutely love it. It's just... We built a telescope the size of the Earth. So we are able to see something that tiny. Wow. It's just stunning, right? Amazing. So I'll end my talk by, well, perfectly an hour. So I'll end my talk by just kind of like teasing you with what's coming up next. We know that a picture of our own Sagittarius star, our own black hole, is coming. I don't know what's taking so long, but it's coming. So this is a picture of our own galactic center in infrared light. When you zoom in, this is what it looks like in the X-ray. So there is some, X-ray activity going on. Sometimes it flares up, which is interesting. But one day soon, I hope in the next year, we should have another amazing picture of the black hole around our galaxy. And we can compare it to the black hole in M87 and see the differences. I mean, they're 1,000 times different in mass. One's active and has a jet. The other one's just sitting there and flaring occasionally, but not doing anything super exciting. I'm dying to know what this picture's like, right? So I'll end the talk by hopefully having excited you about black holes and letting you know that just by absolute coincidence, thank you, Jonathan, for letting me know about this. I was on a PBS Nova show called Black Hole Apocalypse. There's me. And it's going to be on tomorrow at 9 p.m. on PBS. So, I mean, pure coincidence. But if you want more, there's more. So, thank you very much. And I'll take any questions you have. Here's a question.
I'm wondering how come the holes or pictures are black? Because there's so much accreting material around. It looks like they're partially hiding it in the picture.
Yeah.
So happy we're lucky that we see around the accreting material.
No, so that's a really good question. And the best answer is using this picture. So if this is the black hole, right? And this is like, imagine like around the black hole, there's stuff, right? If you're at the surface of the black hole, if you're a piece of material right here that's giving off light, and you're over here trying to look at it, that light can't get to you. So all the light that's leaving sort of the area around the black hole, that's kind of that you would expect to see something, is being curved away. And so you're only seeing the material that's kind of around it. And some astronomers refer to that black thing as like the shadow. It's not really a shadow, it's not casting a shadow. It's just deflecting or just sort of absorbing really the light that would otherwise try to get to you. So there is stuff here, but it's like that light is being pulled in by the black hole. And so you don't get to see it. That's the reason. Yeah. Yeah, you still have a question? Yeah.
Another question.
Sure.
Material approaching a black hole gets accreted into the black hole. When it reaches the event horizon, it disappears into the black hole.
That's right.
Meanwhile, it's getting very bright.
Yes.
So that, again, how can we see a black hole if all this accreting material is, and does it stay out? And of course, it gets slowed down by gravity.
That's right.
So
We never see the black hole. We only see the stuff around it. So when you see a quasar and you see those broad emission lines and you see that bright green light and you see that incredible luminosity, that's like if you walk into a murder scene and you see blood splatter and a weapon, but you don't see the actual murder, you know? You're inferring it's, I'm sorry, that was very macabre. It is a bit like CSI work, you know, you're piecing together a puzzle. And so in general, when we see a quasar or X-rays, we're not seeing the black hole. We never get to see the black hole. And that's why in my talk title I put it in quotes, because, I mean, I guess the most direct evidence.
It looks like in the picture.
That's right. So the absence of light is what you're seeing, right? Yeah. That's right. Yes.
I wondered, this is probably a crazy question. We're talking about 5% of the estimated mass of the universe, right? Dark
I
matter
think
being the rest of it?
Yeah, it's way less than that. The black holes would be.
Oh, no, I just meant the mass that we are dealing with right here.
Oh, our own regular stuff. Yeah.
Yeah, the regular stuff.
That's right.
Where does, in all of this picture, does dark matter fall?
That's a really good question, actually. So it's something that like most sort of baby astronomers think about when they're in grad school, and then like it's something you have to sort of learn. Which is, I always wondered, like, well, doesn't the black hole accrete dark matter too? And so here's an interesting thing. Dark matter, and I could give a whole separate talk on why this is the case, but if you hopefully believe me or trust me, we've done experiments and we have good evidence by looking at galaxy clusters, which are big and have lots of dark matter and give off other light, that unlike regular matter, dark matter doesn't interact with itself. It doesn't collide. It doesn't feel itself. The only thing it feels is its mass. It only feels gravity, okay? And so why don't we fall into the sun? We don't fall into the sun because we are going around in a perfectly nice orbit and nothing is sort of taking away our energy. Nothing is slowing us down. So we stay on our orbit. And so dark matter does the same thing as it goes around the black hole. It just kind of gets into orbit. But so it needs like some kind of friction or some kind of viscosity or some kind of way to lose energy so that it can fall further and further in. So there is dark matter, but it tends not to sort of go into the black hole. There might be like a dark matter particle that happens to be on a perfectly straight radial trajectory. And I forget, there's been some calculations done, and it's something like maybe 5% of the stuff around it might get accreted. It's something on the order of a few percent of like the dark matter surrounding a black hole will be on the right trajectory to not go into orbit, but just go straight in. But all the rest of it, because it has no means of colliding and therefore losing energy, it just stays in its nice orbits, and it just kind of orbits the black hole.
But yet it has mass.
Yes, that's right. It has mass, but it doesn't have, it's collisionless is the term we use. And collisions are a way of transferring energy. Yeah.
I have a little problem conceptually with what is happening in the Milky Way galaxy. We have maybe trillions of stars in the galaxy.
Yeah.
Some are dying. A small fraction are dying.
Yeah.
They're giving rise to neutron stars or to black holes.
Yes.
What's in our galaxy now? What do we have? How many black holes? How many
Oh,
neutron
that's a really
stars?
good question. So I don't know off the top of my head the answer to that question. I should, shouldn't I? You know, so that experiment where we stared at the Magellanic Cloud and we watched those microlensing events,
Yes.
I'll answer your question this way. The reason we did that experiment of staring at the Magellanic Clouds to look for those microlensing events was actually to see how much of what we call dark matter isn't made up of that interesting collisionless stuff, but of stars and black holes and things that are just too dim for us to see by the light that they might emit or not. But we might be able to see them through just them passing over and doing a lensing thing, right? And then you can, if you know sort of what fraction of the galaxy you're exploring, and you count how many of those events you get, and you extrapolate, so on and so forth. And I believe, being in the most generous possible way, they could say that maybe 15% of the dark matter in the galaxy is made up of these exotic types of things like black holes and neutron stars. So I can't give you an exact number, but let's say like 15% of the mass of the halo, which...
It's a very active, if you look at the galaxy, let's look at the galaxy
Yeah.
as just a circle here.
Yeah.
It's a pretty active thing, isn't it? then?
Well, so it's interesting,
But
right? The
because there's
galaxy.
a black hole in the center.
Yeah, so there's a black hole at the center. The galaxy has sort of like an anatomy. I actually taught a first-year seminar on this. It was great fun. To incoming freshmen, so it wasn't at a very technical level. But galaxies have anatomies. So they all exist in these big halos that you can imagine to be spherical and are almost entirely made up of dark matter. If you're a spiral galaxy, there's a disk, sort of, equatorial in that halo. And everything's kind of orbiting and conserving angular momentum and going around just like us in the spiral arms. And stars are being born and stars are dying and so on and so forth. But in the actual halo all around, and then of course there's the black hole at the center. And actually, I should say this, we know that there's a structure that kind of bulges out, it's called the bulge, from the center of the black hole. You can sort of see it in that picture I showed of the Milky Way. Let's see.
Well, that's the shape of the Milky Way, right?
Yes, that's right. I showed you an image of it. Yeah. Let's see. So there's a bulge, and in the bulge is like a whole sort of cornucopia of different types of structures, which is, here we go. So like this would be the bulge. And so the bulge kind of has like old stars, young stars. It's kind of a mess, and we think that that's where, if the Milky Way had had previous mergers, which it might have with smaller galaxies, the bulge kind of grows through those processes. But then out here, I mean, look how empty it is, but you still see there's stars and stuff, right?
Right.
Are extremely old stars, very old. So they kind of represent maybe the first generation of stars that were born in our galaxy. Maybe they represent kind of remnants from old galaxies that we've kind of cannibalized over our galactic history. There's black holes up there, there's neutron stars, there's all kinds of things. But the black hole, sorry, the halo represents kind of like the fossil record of the Milky Way. Whereas in the disk, where it's gaseous and there's lots of young stars, and where we are, the sun, is more like the more recent stuff that's been going on. Yeah, I don't know if that answers your question. I mean, I agree with you. It's a very...
implying that there's dark matter around the outside of the galaxy.
Yeah, so there's dark matter kind of everywhere.
Yeah, but is it like...
It kind of feels like a whole halo. Like imagine like a big spherical mass of mass.
Well, what about the density of the dark matter? Is it different on the outside as compared to the inside of the galaxy?
Yeah,
Or is
so
it just all
such a
spread
good
around?
question. It's one of those things that we're still trying to figure out actually. So it's not a uniform density.
No.
It has some density profile. It's called an NFW profile, we think, but it might be wrong.
Okay.
It's very hard to measure these things.
Okay.
And so actually I will say that there was a satellite put up in space by the Europeans about 4 years ago now, I think. It's called Gaia. And it's an incredible experiment. It's managed to measure the positions and the brightnesses and the distances to something like 1% of all stars in the galaxy, which is, what, 10 billion? 100 billion?
Of all stars?
Yes, yeah.
Yeah.
More nearby than far away, but, depending on the brightness.
Right.
And their velocities. So you can actually make like a little movie of like, where are things going to go and stuff. And the point is, to try to figure out what the there's many points, but one of them is to figure out what the dark matter distribution is in the galaxy and the density and all these questions that you asked. They're really good questions. I don't know that we have a very good handle on these things in the Milky Way. We can do it a little better for galaxies that are outside of our own because it's easier to see the forest when you're not in it, so to speak, But then we don't know other things, like we can't measure individual stars. And so there's a trade-off, right? You gain some benefit by looking at a distant galaxy, and you lose some because, so it's a puzzle. Yeah. Yeah.
I have a question about the interferometer.
Oh, yeah.
One of the things I have a difficult time getting my head around is the fixed speed of light.
Okay.
And your suggestion, it seemed to me the way you mentioned it, was that the light went out, hit a mirror, and came back and slowed.
No, it had a shorter distance to travel. So it went at the same speed, but because the arm length changed, it had a shorter distance to travel.
Okay.
Yeah. Yeah. We could do a whole other talk on relativity. I don't know that I have a quick answer for that one. Yeah. So sure, yeah.
You mentioned a couple times in the presentation about the jets.
Yes.
Talk a little bit about the
Yes.
size of the jets and
Oh, the size. Okay, yeah. So the sizes of the jets can be Sorry, I have to switch to units that are not familiar to me. Astronomers don't use light years. We talk in megaparsecs and parsecs, and what's a parsec, right? If you've seen Star Wars, you think it's time. It's not a unit of time. So let's see, there are 3.3 light years in a parsec, so I have to divide. But okay, so a typical galaxy is like tens of thousands of light years across. Okay, so that's a few tens of thousands of maybe 50, let's say. And so this looks like it's, I don't know, 30 times bigger than that, right? These are one of the bigger jets that we see in the universe. There are also smaller ones. Yeah, they can be on the order of, I mean, I'm trying to think of like, there's a range, right? I mean, this one is on the order of, if this is tens of megaparsecs, this is hundreds and hundreds of sorry, light years. Millions of light years, or thousands of light years, excuse me. But I think, so I thought you were going to ask me a different question. I thought you were going to ask me how do you make jets.
Okay.
We don't really know that either, but the way, so jets, let me not be political. The reason you get radio emission from jets, the reason you see what you see, has to do with electrons that are traveling at relativistic speeds, so near the speed of light, along magnetic field lines, okay? So it's called synchrotron radiation. We can make synchrotrons here on Earth, too. So there, I don't know, like biologists like to use synchrotrons for things. I'm not sure for what, but they do. So we know how to make them, right? What you need to do is you need to create powerful magnetic fields, and then you need to shoot electrons kind of like along those magnetic fields. And what happens is the laws of electricity and magnetism tell us that when a charge is moving or has some speed that's like perpendicular to a magnetic field, it'll get coiled into it. And it'll get put almost like into orbit-ish, you know what I mean? It get coiled. And so here's the interesting thing. When a charge is moving in a circle, it's accelerating, because anything that's not moving in a straight line at a constant speed is accelerating. So if an electron is accelerating around a magnetic field line, an accelerating charge gives off light. It goes as the acceleration squared. And so this is evidence for magnetic fields that are kind of shooting out like this, and then you have electrons that are spiraling out, and they're probably crashing into some intergalactic material here and slowing down all the way far out. That's what we know. Now, how do we make such powerful magnetic fields? That's the thing that we haven't quite figured out yet. We know that magnetic fields can be produced. Let's say if I took a wire and I made a current in the wire going in a circle, I would get magnetic fields that shoot out in straight lines going like that, okay? So there must be some charges that are spiraling around. Well, the accretion disk, that water going down a drain, is a plasma, so it's charged and it's going around in a circle. So that makes sense. It all kind of feels right. But then when you go to do the math, you don't have enough power to make those magnetic fields. So we're still trying to figure it out. I have yet to see a theorist simulate this. They're working on it.
I think we have time for one more question.
Could you comment about the nearest quasar and the distances of the furthest quasars? Do they go back to 13 billion years?
Yeah, yeah. I can talk about that. So it depends on how you define quasar. So I'll start with the furthest. The furthest quasar was just recently discovered in the last year. It's at a redshift of 7.5. I actually was privileged enough to be asked to write about it for Nature magazine. I didn't discover it, but I got to sort of write a commentary on it. So I don't know, you can look it up on my webpage. News and Views. There's a little commentary about it. But yeah, we think we're seeing its light coming to us from a time that's less than 1 billion years after the Big Bang. So the universe is about, I want to say like 690 million years old. It's extremely early. And look, there are a couple of really amazing things about quasars. For example, if I took a spectrum, in fact, we have taken a spectrum of that quasar at a redshift of 7.5 when the universe was a baby, it looks almost indistinguishable from the spectrum of 3C273. They look the same. It's crazy. And so there's something about, and so we can determine the mass of the black hole, and we find that it's several billion solar masses. How do you build, I forget how many, several billion solar mass black hole in such a short period of time? So that really is a challenge to physics. We can sort of barely do it. We can sort of contrive a way of doing it, but it requires kind of turning everything up to 11 for like the duration, if you know what I mean. You have to start off with a small black hole and it has to like accrete at the highest rate for the longest time, and barely not break physics.
But these giant black holes are so far away from us, they should be early. They
Yes,
should be
that's
early.
right, yes.
And they're going slow. Is that right? They're traveling slow because they're not out with everything moving around. Or are they moving?
No, they're actually going very fast.
They're the
Because
fastest.
remember, the further
The
the
further away,
thing,
the
the
faster
faster
they
it
go.
goes.
That's
So
right.
they're going at
So they're
extremely,
So they're early stuff.
yeah, very
They're
early.
Early stuff.
Yeah.
Okay.
And so there's amazing things about that black hole. Like, how did it get so big so fast? And why does it otherwise look like all the others? That's weird. There's no evolution. What's going on? So that's the furthest one, right? And of course, it has to be incredibly luminous to be able to see it that far away. So the reason I said it's a little tricky to say what's the nearest quasar is because quasar is kind of a human definition. You know, the Milky Way has a black hole too. It's not a quasar because it's not accreting that much, but stuff does fall into it occasionally, so it is accreting. And so you have to kind of draw a line. So astronomers draw a line at some luminosity. So it's kind of an artificial distinction. So some might say that 3C273 is the nearest quasar. Some might say that Markarian 231 is. It's another nearby galaxy. So there's a few kind of good contenders nearby. There are galaxies that you can study in detail, and they do have a big black hole that's growing, and it's hard. There are also these other things called active galactic nuclei, which are kind of like the moderate, wimpy-ish versions of quasars. They're just not as luminous, and they're not as extreme, but otherwise everything's the same. They have broad lines, they have X-rays, et cetera, et cetera. So, and those are relatively nearby. Somebody might say that M87 is an AGN. I wouldn't argue with them about that. So